Welcome to Brain Vision.
So for the first part, we are going to use force is equal to I times the cross product of length and magnetic field. And this gives the magnitude to be I times L times B sine phi, where phi is the angle between length and the magnetic field, and direction is given by right hand rule. So we are going to apply this equation to each segment and see what we get. So FPQ is gonna be I times LPQ. So current is basically capital I. So let's write capital I in each of the case. Times B sine phi. So phi for PQ segment, you see that I and B are parallel. So phi is 0 degree and this gives the force to be 0 on the segment. For segment PR, we do the same thing, IPR times the magnetic field times sine. So here they are perpendicular, so this is 90 degree. This gives I times LPR times the magnetic field, and we get this value to be 12 Newton. And by right hand rule, the direction is going to be into the screen or into the page. Similarly, we do the same thing for QR, which is ILQRP times sine phi. This is equal to I times. So LQR is basically this distance, which can be found from Pythagoras theorem because this is basically 90 degree. So LQR will then be equal to square root of the sum of the squares of the other two sides times B times sine phi. So if this is phi, this is going to be 90 minus phi. So this is basically 90 minus phi. So this is phi. That's what we have. So, okay, let's check again. So this is basically phi. So this is 180 minus phi. This is 180 minus phi. So this will give this angle to be phi. Okay. So if this angle is phi, then sine phi is gonna be the perpendicular over hypotenuse. So that will be LPQ over, okay, just a minute. Oh, okay, I think, so let's check this value of phi again. So this is not the angle between I and B. This is the angle. So if this is the angle, then this is, oops, this is the phi that we need. So that is equal to LPR over LQR. So I'll just write that. So LPR over LQR. And QR is basically this value. So let's do this. So this is going to come 1 meter. So this will be 0.8 over 1 meter, and we find the force to be 12 Newton in this case. But the direction is gonna be out of the page. We don't need to find QR actually explicitly because these just cancel out ultimately. So yeah. Now the net force, okay, I just wrote F here, P here instead of F. So the net force is a vector sum of all of these forces. And you see that we have 12 Newton into page plus 12 Newton out of the page. So these, they just cancel. So the net force is going to be 0. So this is the second part. Now for the third part, for calculating torque on a straight wire, we can assume that the force on a wire is applied at the wire's center. And also note that we are finding the torque with respect to the PR axis, which is this axis, and not about the point. And consequently, the lever arm will be the distance from the wire's center to the x-axis. So let's use that. So torque is equal to R cross F, and so the magnitude of torque will be R times F times sine phi, and we apply this to each segment. So RPQ will be R times F, which is basically 0. FPQ from here. So torque is going to be 0 here. Similarly, R torque PR will be equal to R times FPR sine phi. But here R is equal to 0 because the axis is, because this is the axis about which we are finding the torque. So this is 0 R, so torque is also equal to 0. And for torque about the segment QR, we have R. So why am I doing the dot here? So R times FQR times sine phi. So R is basically the center of this from the axis, PR axis. So that is going to be half of the distance of PQ. This is the center, so this is going to be half of the distance of PQ. So that is equal to 0.3 meter. We found QR to be 12 Newton, and sine phi, you see, so this is out of the page and the force, and R is basically on this plane, on the plane of the page. So the angle between these two is going to be 90 degree, and so we get this value to be 3.6 Newton times meter. And so the net torque is equal to vector sum of all these torques, which is 3.6 Newton times meter. And we can find the direction of the torque by right hand rule being applied on R and F. So this is basically R, and the force is out of the page. So torque is basically going to be towards right. Now for the last part, we use torque equal to mu cross B, where mu is N times I times A. So torque, magnitude of the torque will be NIA times the magnitude of magnetic field times sine phi. And phi is 90 degree. So let's just write all the values. So N is just 1 because there is just one turn. I is given to be 5 ampere. I have written that up here. And the area is the half of base times height. So area is half times length of PQ times length of PR, and the magnetic field is 3 Tesla, and phi is basically 90 degree. So we use those values here and we get the torque to be 3.6 Newton meter, which agrees with our result from part C here. And if you take the direction, you'll see that the direction of this will also be, that the direction can be chosen, can be found using the applying the right hand rule on the moment and magnetic field. So if you see that, and if you apply it over here, you'll see that the moment is out of the paper, and sorry, the moment is into the paper and magnetic field is towards upwards. So applying right hand rule to that, we get the torque to be also towards right. So both the magnitude and direction we calculated here agrees with that to part C. And for part E, so we see that FQR is out of the page, and since this is the force that produces the net torque, the point Q will be rotated out of the plane of the figure, because the torque is towards right. So this point is gonna be rotated out of the plane of the figure.